And then I want to talk about how they work. But instead, LSTM tutorial. I want to show you how to find resources on this. As it happens, Cola's blog, which is the top Google hit when you search for LSTM tutorial, has a really good explanation of LSTM models. And kudos to Google for promoting it to be their top link. I kind of recommend you read this page. In fact, maybe I'll put it on assigned readings. I will. The last thing I need to put on our website is some final readings to do. I'll add this to a pile of other things that you get to go peek at in your reading time. But here's his example of, hey, there's a recurrent model, and here's how we unfold it through time. Kind of the same picture as I just drew, right? And here's his example of, hey, look, things in the far past can affect things in the future. Wow, I didn't actually review his blog before I started this lecture, but I should have just used his pictures. A traditional artificial neural network looks kind of like this. That's a weird way to draw it, but he's suggesting there's linear weights in here, but there's mostly a tanh is the only thing that lies between the recurrent connections. And it unfolds like that. Here's what an LSTM model looks like. They have lots of stuff in them, and that lots of stuff amounts to logic. It's kind of like they've used a neural network to build these gates that open and close doors and decide when to allow data to flow through and when to retain it. And when we train these gates by backpropagation, they tend to learn when to open and close, which effectively helps you learn when to remember things and when to just let it slide by and forget it. And this becomes really good at solving time series problems. So LSTM models have been highly effective in all kinds of time series challenges. It's going to give a bunch of examples. I'm wondering if this is the right time. Yeah, so Google has a model called, have you seen Google Translator? You can type in words in any language and it spits them out in any other language. It uses 6 layers of LSTM units, and that's what does all of the translation. It's a highly effective thing for time series problems. So it's kind of worth digging into. And well, just to be short on time, to be short on words to spare time, here's the grand key why LSTM models work. You see how this line that runs right along the top goes through a multiply and it goes through an addition, and it just feeds on right through? Compare that to the old style way of doing it, where as it passes through, it goes through tanh, and then it goes through tanh, and then it goes through tanh, and then it goes through tanh. Basically, the problem, here's the grand intuition behind it all. The problem is the activation functions. When you've got an activation function, it squashes the values, and it squashes the derivative during backpropagation and causes the vanishing gradient problem. If we construct our model such that there's no activation function in the memory, but the activation function only happens in the vertical, forward propagating through the model, then the memory can persist however long it needs to, and yet you can do nonlinear predictions of the outputs that you actually want. And that's kind of the big grand discovery there. And it took years for us to figure that out. But we still need some mechanism of causing our memory to get flushed or get updated. And that's what all this logic here is all about. So let me just describe that a little bit. A sigmoid here is basically the logistic function. This is the Greek sigma function. He's using it to imply sigmoid, and sigmoid is usually the logistic function. Logistic function is just like tanh. All 4 of these yellow boxes here imply that the inputs have gone in, they've gone through some linear set of weights, in all 4 cases, and they're 4 different linear sets of weights, and then have been squashed by an activation function. And in 3 cases they use logistic, and in the 4th one they use tanh, just because, rather the 3rd of the 4th they use tanh, because that's what the authors of LSTM models did. This is a multiply, these are additions. All of these are differentiable operations, and then if you wire them up in this way, it makes a block called an LSTM block. If you build a neural network and you have these in it, it's called an LSTM network. And they can be trained by backprop, and they seem to work really well for time series problems. There's the high-level quick summary. Now let me tell you why I didn't give you an assignment involving coding these up. Okay, I did, but it was worth 0 points and was due yesterday. Ew, right? I mean, they're just not easy to code up. You can do it, it's gonna take you a weekend of sitting there with Kola's blog or some other tutorial and just kind of thinking through, okay, wait, this layer connects to these 2, but not that one, and this other layer connects to this one, and it's a little bit of logistical mess to do, and that explains why nobody's found this sooner. But he goes into some detail as to exactly how to code it up. And yeah, you can train it just by backpropagation through time. And when you do, oh, and here's what a gated recurrent unit looks like. And it's slightly simpler than an LSTM block, but not a lot. And this is the simplest effective recurrent neural network that we have right now. And you can use this to do all kinds of interesting time series problems. And I think that's where I'm going to leave you with recurrent models. Yeah?
So when they train recurrent models, do they really go all the way back to the first?
Yes and no. You actually do have to go back at least as far as might possibly be affecting the present. Does that make sense? Usually there's a parameter, we'll just call it k. If you unfold for k iterations, then you're making the assumption that never in the history of the universe does anything cause ripples of effect more than k time steps into the future. And if you want a universe where anything in the past can affect the present or the future, then yeah, you really do have to backpropagate all the way through time. What they have, so this particular portion of the LSTM model, this path that has no activation function that just passes the memory straight through, this has a term, this is called an error carousel, or a memory carousel. The idea is it's kind of like your memories get on a merry-go-round and they just go around in circles. They're recurrently feeding through the model. And because there's no activation function, the error that gets propagated back through time doesn't get diminished unless this sigmoid gate that controls it gets turned on. And so it can propagate arbitrarily far back without the gradient vanishing and can therefore learn to remember things for however long it needs to. Yeah?
The other question I had was, since it also outputs your continuous M vector, does that just have no blame? I mean, how do you just not do anything with that?
Let me, continuous M. Oh, my M. Yeah, so that thing I called memory, this thing that's being passed through, it actually gets blamed through the following path. So H is what they've called their outputs. If you look, that gets backpropagated down through here and then up through here and passes through that multiplication and then through that tanh and then connects to that memory. So some of the blame does go into here and updates what's in the memory. And that backpropagates down through all of here and back to the input. So there is a path through which everything does get updated, yes. I guess I want to also describe the function of these 4 gates, just so you see those. Let's look at this first one. This is called the forget gate. The idea is, if you turn it off, turn it to 0, the memory is going to get multiplied by 0. What is that going to do? It's going to forget everything. So this thing learns to activate only when the input suggests that, hey, it's time to flush my memory. This one tells you when to remember something, because whatever comes in, when this one activates, that multiplies this thing by 1 that gets added to your current memory. So this is the remember switch. This is what to remember switch. So takes your inputs, munges it in some linear way, runs it through an activation function, and that's what it puts into your memory. This one is your output gate. So basically when this one activates, then what's in your memory gets fed into your output instead of what gets fed through from your input. And if you kind of think about it, those are kind of the operations you use in a memory chip, right? You read to your memory, you write to your memory, you flush your memory. Of course, read and write's just enough, but well, we do it with 4 operations. So this thing kind of, sort of in fuzzy continuous land learns to gate the flow of information such that it can remember or forget things. And it's a cool model. If you were to plug into, say, TensorFlow, you would find LSTM models already implemented for you. So all you really have to do is build your neural network and think to yourself, are there temporal components of this problem? Oh yeah, let's throw in some LSTM layers. And then you call the train method, which is already implemented for you, and it just trains it, and then you say, yay, now it works better. And that's about as much as most of you will ever get into LSTM networks. But if you actually want to implement one, then that would be totally awesome. Okay. Yeah?
If you go back to your diagram of the recurrent neural network.
This one?
Yeah. So
okay.
You enrolled that for like 6 steps. I thought each unit had the same copy of W, and you were kind of just kind of like
yeah.
the shared weights in convolutional neural nets.
Yeah, that's a really good analogy. Remember in convolutional neural nets how it's the same weight, and yet different error signals are updating them, and we just add all of their influences to them. So as all these different outputs produce their error signals, and yes, even though the error signal is different after each pass, they're kind of adding to the same weights again and again and again. And that does create a necessity of using a slightly smaller learning rate, because otherwise you might update the weights way too much, and you have to, although presumably the error will vanish away at the time it's supposed to because it learns to control it properly, or something like that.
I thought the weights in each component were all the same by design, and so they're updated by tandem and not just kind of like, oh, they're close to equivalent, but not.
Oh, no, you would only have one set of weights in your computer, in your memory. And so, yeah, they are all updated. But because you've unrolled through time, when you're backpropagating, you're kind of at some position in this process. And so it's kind of like, first you'll update these weights, then you'll update those same weights, and then you'll update the same weights again. And see, so I guess in real time, the weights go through an iterative process of being updated, but it's as though as soon as you saw that output, you just updated the one set of weights according to the cumulative effect that it should have. If that makes sense. Okay. Okay, well, there you go. This is what makes recurrent neural networks effective.